The last speaker of this session is Hassani, who will talk to us about how to optimally quantify uncertainty for risk-averse agents. All right. Hi, everyone. I'd like to thank you all for attending the talk. Also, thank the organizer for giving me the opportunity to speak here. So the talk will be about uncertainty quantification for risk-averse decision making. And this is a joint work with our excellent students, Shai and Kiani, as well as George and Aaron. We are all members of, we are all at Penn, but we are also members of this Encore Institute. So this is like a whole Encore product. So, so before diving into the main details of the talk, I'd like to give you an overview of how we think about predictions and on its connection to uncertainty quantification, specifically when there are downstream decisions or actions to be made. And so the main point here is that, I somehow hear myself here. Yeah, okay. So the main point here is that decisions are often fundamentally based on actions. And in specifically any application that you can think about, when you want to make decisions, there will be beforehand predictions about the environment. And those predictions will guide the decision. So for example, consider the application of driving, whether or not it's done by a human or let's say by an autonomous system. Every decision that's done here is based on predicting what the environment surrounding the car is. Okay, for example, let's assume that you are at an intersection and you want to decide whether or not to accelerate. So you would look at an object in the sidewalk, so let's assume that there is an object in the sidewalk. You would first have to predict what that object is. And based on what your prediction is this a human, is this, let's say, a tree, is this a trash can? Based on your predictions, you would essentially decide to make what actions you have to choose, right? So for example, you would accelerate or not. And so this is one application. You can think about other applications, for example, clinical medicine, where let's assume that there is a model or a doctor which has to decide based on the patient and the information, let's say the MRI scans that have been obtained from the patient. And so based on the information, the model or the doctor first has to predict about the ground truth, about the disease that the patient has. And based on the disease or the set of diseases that the patient has, the doctor will then make some downstream action, for example, some treatment or some further tests to be acquired. So the point I'm trying to make here is that decisions are fundamentally based on predictions, or in other words, predictions fundamentally guide action. And this is when this is the case, often when predictions are based on ML models, this question always comes up that, can we trust the prediction? If the predictions have errors, can we trust these predictions, or also can we trust the downstream actions that are made based on these predictions? Okay. And this question is becomes much more important when we consider safety critical applications. For example, applications like this, like driving, or let's say clinical medicine, where deciding based on wrong predictions can lead to catastrophic outcomes. Okay, and I'm sure we have all seen examples or videos of self-driving cars, like Tesla self-driving cars crashing into people or into other cars, and that has been studied quite extensively over the past few years. More recently, we are seeing studies of this type for applications, for example, clinical medicine, which are based on, let's say, LLMs, ChatGPT, and so on. And similar studies show that if you want to trust these kind of models, if you don't trust them fully, then there are problems. There are catastrophic outcomes that have been shown and have been studied. Okay, so these kind of recent works, essentially frame trusting in LLMs as a double-edged sword, which I think is obvious for everyone. So going back to our framework, our bigger picture, so predictions guiding action, there seems to be other factors that would influence this picture. Specifically, there is safety and utility. Okay, we want to design decision-making systems that are safe, that satisfy our safety critical constraints. On the other hand, you would like to design effective systems. You want to maximize performance or utility. And these two notions are oftentimes at odds or in trade-off with respect to each other. For example, on the one hand, you could do nothing and be ultimately safe. And of course, that leads to zero utility. On the other side of the spectrum, we could completely ignore safety, right, and maximize just your utility without considering any safety constraints. And well, that leads to a good utility. However, your system that you have designed might kill a few humans on a daily basis. Okay, so disastrous happen. So what we are looking at is kind of a framework like this, where on the two sides you have predictions and actions, but in between you need principal uncertainty quantification modules to quantify the uncertainty of the predictions. And based on these uncertainty quantification modules, you want to design your decision-making algorithm. Predictions we are going to consider to be based on some ML models, deep neural networks, classifiers, recommendations based on elements, and so on and so forth. And remember these two notions of safety and utility that would essentially influence the design of these two blocks. And so the question that we want to ask is, what's the optimal way of designing these two blocks here, the uncertainty quantification blocks as well as the decision-making block, such that we can navigate this trade-off between safety and utility in applications that are safety critical, high-stakes applications. Okay, so that's the quick question that we want to ask. Now, speaking of uncertainty quantification, there are, in machine learning at least, there are two frameworks to essentially quantify the uncertainty of prediction. One is conformal prediction that I'm going to introduce and talk about. The other framework is the framework of calibration, calibrating decisions, calibrating the predictions of a model. I'm not going to talk about it. At the end of the talk, I'm going to mention how calibration would come into this picture that I mentioned in the previous slide. All right, so I assume that a portion of the audience is not familiar with conformal prediction. So what I'm going to do is to give you a broad sense introduction to conformal prediction. And then we're going to see how action will come into this picture. Okay, so what is conformal prediction? Typically, well, if you want to train ML kind of predictive models, we typically gather some data sets, some large data sets these days, and some large models, and we train the model using the data. Okay? And for the trained model, it could be a classifier, it could be the large language model that gives you recommendations and so on. From now on, I'm going to consider it as just like a blue or a black box, the trained model. Let's call it the trained model. And at test time, when a new data point is given, for example, here, the point X, which is a human walking on a crosswalk, the model, in order to essentially predict what the label this input has, the model will first assign to each class a number, which we call the estimated likelihoods of the model. And so these are some numerical values. And typically what happens is that you would choose the class with highest likelihood as your single kind of label prediction. Okay? That's the typical practice in predictive models. Right? And well, data points that you see at test time have different levels of difficulty. Let's look at these pictures here. And the difficulty increases from left to right. So this one is a human, there's no other objects in the street. So this is easy to essentially classify, and the model assigns a very high likelihood to the right class, which is human here, 99% likelihood. This example is a slightly more difficult. There is a tree in the background. So the likelihood that the model essentially assigns to the human is slightly less, 0.9. The likelihood of the tree is higher, and then there are other classes that have higher. Now look at this example, which is sort of a difficult example. Now for this example, the model assigns relatively high likelihoods to tree and human, but human is the second. So when deciding according to highest likelihood outcome, the model will make for example, will make a mistake on the most difficult kind of example. So that's the usual classification kind of procedure that we have. Okay, and the point that I'm trying to make here is that typically these trained models will give us some estimated likelihoods. These are somehow heuristic notions of uncertainty. These estimated likelihoods are informative. Okay, so there is a model has been trained using a large amount of data. So it gives us something informative, but it's not always correct. Right? And we have to somehow do uncertainty quantification to somehow correct this kind of bias in the model. So what is conformal prediction here? Let's go back to the difficult example. So this, the right class here was ranked second, so it wasn't the highly likely class. Conformal prediction aims to give you a set, which we call a prediction set, instead of just a point-wise prediction. Okay, so in this case, the set would be maybe the first two classes of the highest likelihood, right? And the goal of conformal prediction is, well, as I said, for every input X, it will give you a subset of the labels. You want the subset to be as small as possible, of course. But what you hope is that, or what you want to guarantee is that the probability that the true label belongs to the set is very high. Okay, and I'm going to formalize that in a minute. Okay? So, so going back to our three examples of different difficulty. So this was how just the pointwise prediction would perform. Now, if you give me prediction sets instead of pointwise predictions, then the true label will be in each of these examples, the true label will be from. Okay, so that's conformal prediction. We want to also, what's important here is that typically conformal prediction comes with rigorous guarantees. So we will show that the probability of having the true label inside the prediction set that we construct is very high. Let's say 99%. Okay, provable. Okay, rigorous. So how does conformal prediction construct these sets? So these sets will be constructed using the pre-trained model, as well as a small, relatively small portion of data, a new set of data points, whose size is small relative to what we use to train the model, which is called the calibration. Okay. So what we are looking at is the following kind of block diagram. So we have a feature space X, we have a label space Y. So the input X would be a member of the feature space. It goes through the model gives you prediction. Conformal prediction appears as kind of a wrapper around this ML model and takes as input the predictions of the model and gives you a prediction set, which is the subset of the data. Okay. And so the kind of guarantee that you are looking at would be the following kind of guarantee. So we want to construct these prediction sets in an efficient way using calibration data, whose size is not too large, such that this is the simplest guarantee in conformal prediction, such that the probability that for a new data point, for a new data point pair, X and Y, the probability that the true label falls into the set is large. Okay, so 1 minus alpha is the user specified value. Think of it as 90%, 95%. In extreme cases, you have 99%. And this probability over is the choice of the distribution. Okay, so that's the guarantee that we want. This is the simplest guarantee in conformal prediction. It's called the marginal guarantee. Of course, there has been extensive work on other types of guarantees, but this is the simplest that we want.
But there has to be,
Yes.
There has to be some guarantee on the side. Like
yes, I'm going to talk about that. Okay, so there is a trivial solution here, which is the full label set, and we have one. But typically, in conformal prediction, you want to have sets of the smallest size because you want to get more important. Okay, we're going to get back to this. Yes.
So the prediction here is the distribution of the label, not just the top.
No, not just the top. So the model would give you some kind of heuristic likelihoods. You want to use those to construct predictions. If you just wanted to do like a single prediction, you would just take the top one.
Are there any guarantees, like if the test and train distributions are not quite the same, that you actually reach marginal coverage?
Yes, so it depends. Okay, very good question. So it depends where, I guess what you mean is that the test and the calibration distributions are different.
Like it's crucial, it's not a point-wise guarantee that like
yes.
for an individual thing.
So,
coverage.
right, so there are different methods for conformal prediction. So if the test and calibration data, so these kind of guarantees typically are obtained where calibration and test data are coming from the same distribution, meaning that calibration is somehow the out of distribution data that you want to in the environment that you want to collect. And remember, calibration data is different from training data. It's a small data set that you gather. Typically, the size is 1,000, not more. Now, there are works on conformal prediction that extend this framework to distribution shifts that you do not experience in calibration data. This is called conformal prediction under distribution shift, like covariance shift and so on and so forth. The algorithms there are considerably more difficult more complex, and the results are less appealing than this one.
There's one more question. So, if I understand correctly, it takes in a sequence of logic.
Yes.
Right? And all that is doing is finding the right threshold.
I'm not talking about that.
It only finds a threshold, right?
That's as simple as that word. Yes.
But is there one that okay.
Yeah, we're not. Yes.
You're right, yeah.
So the randomness of the calibration data is handled with 1 minus alpha.
So the randomness of calibration data is, so, okay, this probability is over the randomness of calibration data.
And randomness of calibration data and also this new data point to be predicted.
Yes,
Okay,
yes.
so I get it.
Yeah, I don't want to make this more
It's only
complicated, but
specify the.
yes, but you're right. The probability is over every random. Okay, good point. Okay, but this makes it very complicated. I had it, but then okay. All right, so, well, let me just tell you that without knowing the simplest solution that conformal prediction provides, this problem looks like a very difficult and high dimensional problem, right? So for every input X, you want to assign a subset of all of the labeled space. So if the size of the labeled space is 20, if you have 20 space, the number of subsets would be 2 to the 20, that would be 1 million, right? So essentially you are mapping every X to a 1 million dimensional vector if you have only 20 labels, let's say, at your space. So beforehand, it would look as like a very complex problem, high dimensional problem. Now we're going to talk about an algorithm, the simplest algorithm in conformal prediction, which, as Sujay said, is some kind of a thresholding, which essentially reduces this high complex problem into essentially calibrating a one-dimensional parameter. Okay, I'm going to explain this algorithm. It's the basis of many algorithms in conformal prediction. It's good to know because we're going to use some of the primitives later on. All right. So let's go back to our example. Okay, so you have a model. The model gives you likelihoods on each of the classes labels. Now let's for a moment assume that your model was completely exact. Okay, so it would assign probabilities. Let's not get into the complexity of what probabilities mean here, but let's assume that it would assign probabilities, and these probabilities are exact. These are true probabilities. Okay, so you have an oracle that gives you the true probability. Okay, and let's assume that these are the numbers that the oracle has assigned, and you want to get a 90% coverage guarantee, a set with 90% coverage guarantee. Assuming that you have the exact probabilities, what would you do? Okay, I mean, the natural thing to do is to start from the top label. These are not true probabilities. I'm just assuming that for a moment. So I add these probabilities until I get to 90%. So 35%, 35, that's 0.7 plus 0.2, that's 0.9. So if I choose these three labels, so the top three labels that have the highest probability, I would get 95, exact 90% guarantee. Right? And since I have assumed that these are the right probabilities, this is the right set by definition. Okay. In other words, if you had access to the exact probabilities, whatever that means, finding the optimal sets, optimal prediction sets would be very easy. Okay. You would just threshold your probability values until the point that the sum of the probabilities become your 1 minus alpha, let's say 90%. Okay, is this clear to everyone? Okay. So, well, more formally, you can define a score function that assigns a value, a score value, to every y, right? Every value of y. This score value is just sum of the probabilities above you. So the score of tree in this case would be 0.35. The score of trash can would be the sum of the two, 0.7. Score of a human would be sum of the three, everything above you, 0.9. And your set would be the following. Every y whose score is less than 1 minus alpha would be inside the set. Okay, so 1 minus alpha is 90%. So every y whose score is less than this value, this will be all these three values of the label, or will be inside the set. And that's exactly this threshold. Okay, so this structure of prediction set, if you had the right probabilities, would make sense, would be the optimal set in terms of length that you would take. Okay, so that's the ideal scenario. Of course, you don't have the exact probabilities. Instead, you have a trained model that gives you estimated values, likelihoods, which are heuristically make sense. They are not exact, right? So the question is, what would you do, right? So, and remember, so we have a we have an interesting way of designing prediction sets, which are of this form, a score being less than some threshold. So the natural way to essentially relax is the score function, which was defined based on the true value probabilities would be the following. Instead of the true probabilities, you would use the numbers proposed by the model. Okay, so I just changed P to pi, where pi is the likelihood outputted by the model. That's also a score function. Okay, and so this is called the non-conformity score. If you think about it, the less the score is, the smaller the score is, the less is the model's uncertainty about it. Okay, so it's like a non-conformity score. So if it assigns a smaller score to a y, this means that that y is very much conformal, very much expected given the input. And if it's large, this means that that y is actually very surprising given x. That's why it's called the non-conformal. Okay, so well, what we want is to again threshold this score like before, but this threshold here is q won't be 1 minus alpha anymore because our model is not exact. These values are not like the sum of the actual probabilities, right? So what we do in conformal prediction is to find the right value of q such that we get the marginal guarantee. Okay, so we calibrate this threshold. All right, so how do you calibrate this threshold? Actually, that's very easy. So remember, you want the marginal guarantee. So you find q such that this marginal guarantee is met. Okay. So let's see. So that's how the structure of your set looks. So in this way, probability that y falls into the set C of x, this is equal, just look at this one. This is equal to the probability of the score being less than the threshold. And now look at the score as sometimes as the random variable, s of x, x, right? Y come from the distribution. So, but this, and you want this to be exactly 1 minus alpha. This equation just tells you that q is the 1 minus alpha quanta of the distribution of s. Okay, something very simple. So again, if you had the PDF of s, q would be just the 1 minus alpha quanta. Okay. But in general, you don't have the PDF of s again. What you have is, let's say, n calibration data points, for which if you compute the score values, that give you n IID points, IID samples from the distribution of n. Okay, then the idea of all these basic conformal prediction algorithms would be to estimate q using the empirical quantile of this distribution. And by empirical quantile means that you just sort this sequence, look at the value at position 1 minus alpha times n, that's the empirical quantile. Let's call it q hat, and your set would be just, so this is, q hat is the empirical quantile, and your set would be just s being less than q hat. And you can prove, it's not hard, if you have followed so far, you can prove that with this q hat, you would get the marginal guarantee. Actually, you would get 1 minus alpha on the other side, plus something that's very small, 1 over the number of shine. Okay, so there are two important points here. Okay, first of all, this problem of designing prediction set has boiled down to estimating a one-dimensional parameter. That's very important in conformal prediction. So you have a very simple way to calculate your sets and get rigorous guarantees. Number two, the procedure was to first solve the problem, assuming that you had the actual probabilities, find the optimal solutions, and then relax or replace the actual probabilities with what the model gives you. Okay? And that was the set. And fortunately, you're able, despite this approximation, you're able to calibrate your set and get some rigorous guarantees. All right, so that was the introduction to conformal prediction. So going back to the relation between this conformal prediction and uncertainty quantification, in conformal prediction, typically we look at the length of prediction set as a measure of uncertainty about the input. So going back to our examples, so look at the size of the set, prediction set. So on easier example, the size is 1. On the harder one, the size is 2, right? So intuitively, what's believed in conformal prediction is that as the difficulty of the input grows, the model will be more uncertain about what the label is. And because of the model being more uncertain, the size of the prediction, there are more elements to be put in the prediction set, so the size of the prediction set will. So the length of the prediction set would be a good indicator of the uncertainty of the model for the length. Yes.
Before we go into this one, this is per sample by sample, I mean,
Yes.
this one, but I guess between the true probability and the model's output, I guess if you're having access to the true probability, probably the Q you can find from the same algorithm will be the optimal Q. While if you're having some model output, then the Q is always higher, I guess. You have to
Higher or lower?
higher or lower, whatever it is.
So it depends on the model. You cannot say for sure.
I guess a threshold,
So the Q is threshold, you're saying, right?
yeah,
Then
oh,
one is
so it
on.
depends on the model.
Depends on.
I have the same
Oh, I
question
see.
about the size of the prediction set, so
Yes.
it can be bigger or smaller,
Yes,
right?
yes.
But you want that to be as close to the original one?
I mean, if it's one, this means that, and if the prediction sets are actually good, both highly multi, it's the true length, right? But typically what happens is that the size is larger than one, okay, and you want it to be as small as possible. But the length is somehow reminiscent of the difficulty of the exposure.
Do you measure, like, in some examples, the size can already be big, because maybe it's very
Yeah,
confusing.
could be the whole set.
Yeah, could be the whole
Yeah.
set. So, and then you will get I mean, whatever you do, you get the whole set.
Yes.
But it is still good, right? So how do you?
Yeah, so you design your prediction sets to minimize the length. So what I mentioned is the simplest algorithm. There are tons of conformal predictions.
Would you not take the difference, like the excess length type of thing, as opposed to?
No,
Okay,
okay.
because in learning, usually like, if it's
Excess
hard,
between
yeah,
the-
excess between the, like, would that not be the?
Yes, there are one or two books that look at the problem in this way. So it's called CQR, the algorithm, but we can do that one. All right, okay, so the point here is that going back to applications where there are downstream actions, like safety critical applications that we talked about, I want to argue that, and this has been observed also in performance prediction in the last couple of years, that length is not the right thing to consider, okay? So let's go back to like the clinical medicine kind of example. Let's consider these two sets, okay, of labels. Okay, so this one has size 4, this one has size 2, this one has a smaller size. Okay, so you would guess that, okay, this one would lead to maybe less uncertain kind of inputs compared to this one. But if you look, this one has cold and lung cancer, right? It's a random set. And from the viewpoint of the doctor, from the viewpoint of the actions, this is like a highly uncertain set. Okay, what actions do you want to choose here, right? Whereas this one, I mean, these are roughly from the same family, so you would kind of come up with actions from the same family. So even though this one has a larger size, or this one has a smaller size, it's uncertainty, when viewed in terms of decisions or actions, is more than this one. We could think about, again, another example in whatever autonomous systems. If you look, the size of this set is 4, but all the labels in it are static objects. So you would decide to accelerate, so a single action, based no matter what you see, which one of these labels are the true ones, okay? You go, so nothing moves here. Whereas this set has a smaller size, however, it has a moving object and it has a static object. So again, you have uncertainty about your action, okay? Which actions do you choose here? Okay, so again, this set has a smaller size, but it's more uncertain with respect to the action. So the point here is that if you want to do uncertainty quantification, this intuitive notion of length is not the right notion anymore, and uncertainty quantification in these cases has to be informed by the downstream actions that you. All right, so then this brings us back to conformal prediction, and then it makes us think like or ask the following question, like what are these prediction sets that we are designing to? Okay, so in particular, there are 3 kinds of questions that we are asking here. Number 1, what kind of downstream decision-making tasks are there such that prediction sets are the right way to communicate uncertainty? And what we show is that for risk-averse kind of decision-making problems, predictions are actually the right way to communicate uncertainty. Then another question is, well, if I give you prediction sets, okay, how do you decide based on these prediction sets? And it turns out that there is, as I will explain, there's a single max-minute policy that's optimal. And finally, how can you derive the optimal prediction set? That's something else that if I have time at the end of the talk, I'll talk about. Okay, you can characterize the optimal set. But So let's go back to the mathematical notions here. So far for conformal prediction, I had just a feature space and a label space. Now we have decisions, so you also have an action space. Okay, again, examples, just one example in clinical medicine. So X would correspond to features or information you obtain, measurements you obtain from the patient. Y would be the true label, the true disease that the patient has, and A would be the actions that the doctor or the model would do. Okay. We could do the same thing for tons of other applications. Essentially, every decision-making application could be considered, where there are predictions, could be considered as this parameter. All right, now, so in decision theory kind of literature, typically we consider a fundamental notion called the utility function, which assigns a value, a numerical value, to the actions and the labels. Okay. And this utility map essentially captures the preference of decision maker in making decisions. Okay, so you would want to go with higher utilities, but you have to be careful. And so the order of things also matter here. So as a decision maker, you take X as input, right? You observe X. Right? However, you don't observe Y. You don't observe the ground truth. You don't observe. As a doctor, you don't observe what disease the patient has, right? So Y is not observed, and only based on X, you take an action. So your action policy depends only on your input X and should not depend on Y. You can predict Y, but prediction of Y is only dependent on X, right, usually. So you have a model, X gives you, let's say, predictions. And once you make, take the action, then your utility will be realized based on the whatever Y was created wrong. Okay, so that's how the order of things is here. Okay? And as I mentioned, you don't observe Y, that's crucial to note. And instead, typically your decisions should rely on some uncertain predictions that estimate Y, and based on that, you would essentially make action. All right, so what is a risk-averse decision maker? Okay, so longest story short, a risk-averse decision maker would like to optimize the quantize of this utility compared to the expected utility. So in other words, to be risk-averse means that I would want to avoid catastrophic cases, which translate into actions that give me very low utilities. So for example, if you're a doctor, the patient has cancer and you tell the patient to go home, that's a very low, like maybe minus infinity utility, right? You want to avoid this, right? So this might happen with a small probability, so it may not contribute to the expected utility, but these actions you want to avoid. So that means that you have quantized. So you want your utility to be higher than some specific threshold with high probability. So you work with quantized rather than just expected rewards, expected. Okay. So for each action policy, you would assign a utility certificate, and this is essentially a safety guarantee that you want your utilities to be higher than some function nuance. Okay, so the optimization problem that the risk-averse decision maker wants to solve is the following problem. So you want to essentially find the action policy that maximizes the quantile utility that you would expect. Okay, so that's the optimization problem that a risk-averse decision maker wants to solve. Okay, so this is the core optimization problem. Now, I want to talk about, so there is no prediction sets here. There's nothing like uncertainty quantification. I want to view this problem from the viewpoint of prediction. Okay, so let's assume that you have a system like this. There's an ML model gives you prediction sets, and the decision maker has to decide based on this prediction. The question is, what's the optimal action that the decision maker has to do instead of predictions in order to essentially maximize this quantile? Okay, be risk-averse but maximize. Let me give you a quick example. Okay, just to see what's the intuitive notion of an optimal design here, and then we're going to quickly maybe wrap up the talk and giving you the final thing. Okay, so let's assume that you are driving, okay, as a human, and there is some pedestrian here, right? And you have some uncertainty about this pedestrian. So most probably the pedestrian is standing there, it's not moving, but there is a small chance that this pedestrian would move. Okay, so your prediction set would be something like this. Okay, standing or walking both happen to be in the prediction, because let's say there's 20% chance that the pedestrian might move, right? So now, what kind of, as a driver, how do you choose your action if this is your prediction set? I mean, you would go with the worst case if you're a rational driver, right? So going with the worst case, this means that you would essentially apply a max-min policy. So you go over worst case elements inside the prediction sets in terms of utility, and you find the action that maximizes the worst case. And that's an intuitive thing to do, or at least as in like safety critical kind of decision-making scenarios. It turns out that actually this is optimal. Let me just skip the theorem, but essentially what we show is that if you're given prediction sets and this type of decision rule is minimax optimal over essentially over all the distributions that give these prediction sets with marginal guarantee. So, okay, I'm gonna just wrap up. So, given that, so the optimization problem that you have to solve once you are deciding based on prediction sets would be the following optimization problem. So this is the optimal action rule that I mentioned, the max-min prediction rule, and you want to essentially design prediction rules that maximize this optimization. Okay, now let's look at these two optimization problems. Okay, so one is maximizing over all possible actions, all possible action policies. That's the actual problem we want to solve. This is another problem based on prediction sets, but this is very conservative, right? So it's just taking the most conservative actions every time based on the prediction. So it's not clear if this problem, solving this even provides a good solution to this one. Okay, this is overly conservative, just a single policy. But actually, it turns out that you can prove that these two problems are equivalent, right? In the sense that if you design the right prediction set here, you would get the optimal solution of it. And the proof is actually very simple. However, the equivalency of these two is very important because it tells you that to be risk averse, you only need to work with prediction sets. In other words, prediction sets are the right way to characterize uncertainty of the predictions, and that designing the right prediction set gives you the optimal value. Okay. So, so these are the two questions. Another point in the talk that I don't have time to go through is how you solve this optimization problem, how you design the optimal prediction set. And that can be done, let me just skip the details, by some duality theory. But in the end, what is interesting here is that the optimal prediction sets are still characterized by a single one-dimensional number, like before. And that number you can calibrate to find the optimal. Okay, so just the last slide. Okay, algorithm finite data. Just the last slide. So for risk-averse decision making, what we showed is that the right medium for communicating uncertainty would be prediction sets, and the right decision rule would be the max-min decision rule. Okay, so these are the details. Now, for risk-neutral decision makers, that's the part about calibration. If you want to ignore safety and just focus on maximizing expected utility, it turns out that the right medium for uncertainty quantification would be calibration. So you just make sure that the probabilities outputted by the model are somehow calibrated, are the right probabilities. And the decision making would be the best response decision making. This is a classic work in the finance literature, works by Boer and Foster and so on. So I hope these two messages are somehow conveyed. Thank you.
Let's take questions during the break. We have a 10-minute break now. We're going to start the next